An electric field is a disturbance in space created by the presence of electric charge. The electric field at a particular point in space can be defined as the force per charge on a test charge at that point in space. For a single positive source charge as shown, the force and hence the electric field depend upon the position of the test charge. The field exists at every point in space regardless of whether there is a test charge there to sense it. An array of vectors can help visualize the field. These field vectors reflect the symmetry of the charge. In this case, they show the field is directed radially outward from the positive source charge. Electric field lines are another way of visualizing the electric field. Field lines are continuous lines that are tangent to the field at every point in space. That is, field lines are parallel to the electric field. The concentration of the field lines in a region of space is an indication of the strength of the field. The field lines will also reflect the symmetry of the field and of the distribution of charges that produce the field. For a single negative source charge, the force in the positive test charge is attractive. As a result, the force, and hence the electric field, will now be radially inward. As was the case for the single positive source charge, the field resulting from a negative source charge is spherically symmetric. For the positive source charge, the field lines came out of the charge, while for the negative charge, the field lines go into the charge. In general, electric field lines will start on positive charges and end on negative charges. The net electric field due to multiple charges is the vector sum of the contributions of the individual charges. For the two positive charges shown, the field reflects the symmetry of the charge configuration. Far away from the charges, the field acts essentially like it was produced by a single charge. In this case, there is a positive charge and an equal but opposite negative charge in a configuration known as an electric dipole. The test charge illustrates the net effect when the test charge is repelled from the positive and attracted to the negative. Near the positive charge, the field is directed outward from that charge, while near the negative, the field is directed inwards. The field gets weaker much more quickly than when there was a net charge. The general rule that field lines start on positive charges and end on negative can easily be seen here. The pattern of field lines is characteristic of fields due to dipoles. A water molecule can be modeled as two positive charges and a double-strength negative charge so that the molecule has no net charge. For points in the interior of the molecule or in close proximity, the resulting electric field due to these three charges is more complex. Away from the molecule, the field takes on the characteristics of a simple dipole. As such, water is said to be a dipole molecule. A line of charge, here simulated with an array of closely spaced positive charges, has axial symmetry. Close to the line segment of charge, the field is approximately radially outward from the axis of the line. At points much closer to the line than to the endpoints of the line, this axial symmetry improves. In the idealized limit of an infinite line of charge with a finite charge per unit length, the field lines would be expected to be directly radially outward from that line of charge. A parallel plate capacitor consists of oppositely charged conducting plates, simulated here by two flat arrays of charges, one positive and one negative. The field is strongest between the plates and is very weak outside that region. Between the plates, the field is nearly uniform. The uniform field is represented by parallel, equally spaced electric field lines. The field lines shown here bend outwards a bit at the edges of the plates, an effect known as fringing.